Hello everyone, I am Wook-Hee, a postdoctoral associate at Virginia Tech. Today I'll talk about our paper, PACTree, a high-performance persistent range index using PAC Guidelines. This is a joint work between Virginia Tech and EPFL. This is the outline of today's talk. Let me first explain the background of this work and introduce our design guidelines, PAC Asynchronous Concurrency Guidelines. After that, I will explain our high-performance persistent range index PACTree, and then I will show you our evaluation results and conclude this talk. Let me first introduce NVM and its architecture. The multi-memory is available now, especially Intel-Optane DC persistent memory is the first commercially available NVM in the market. The interest in NVM is rapidly increasing because it provides byte addressability and durability with high performance. Also, it has a huge capacity. The current generation of DC persistent memory can provide up to 3 TB per socket. More interestingly, it provides direct access to the NVM using load and store instruction. Let me explain the architecture of NVM in detail. This is the current processor's architecture. If a system has NVMs, they are attached to each socket. When NVM writes are requested, the write operation will be inserted to write pending queue, which is in the persistent domain. I/O granularity between the memory controller and obtained DIMM is 64 bytes, which is the size of a single cache line. In the obtained DIMM, there is a 3DX point media, and the address indirection table and the data are stored in the 3DX point media. The XP controller merges consequent I/O request using XP buffer. So, the I/O requests to 3DX point media are triggered at XP line size granularity, which is 256 bytes. Also, if a core requests the data to the remote NVM, the directory cache coherence information in 3DX point media is updated. As you can see in the previous slide, NVM is more complicated than we expected. There are some research efforts to analyze the NVM hardware characteristics, and it is known that the limited bandwidth and slow latency of NVM is the fundamental limiting factor in designing storage systems. However, it is still unclear the implications of NVM for storage system design. In this work, we investigate performance properties for NVM and explore their implications for index structures, which is the core storage system design. Let me introduce our design guidelines, PAC Asynchronous Concurrency Guidelines. Let me first start with the NVM software stack. An NVM allocator creates a NVM heap, which is essentially a large file on an NVM file system. The NVM program can access the NVM hardware using load and store instruction. For NVM allocation and deallocation, the NVM program uses an NVM allocator to manage NVM space in a crash-consistent manner. In this work, we thoroughly analyze how prior persistent index work on the real NVM hardware. Based on the analysis, we propose design guidelines named PAC Asynchronous Concurrency for high-performance persistent index. From the empirical analysis, we derive 5 findings on NVM hardware. We then propose 10 guidelines on the use of system software, algorithmic considerations for persistent index, and concurrency control for making the best use of NVM hardware. Due to the time constraint, I will introduce 2 guidelines for saving the NVM bandwidth today. Let me first explain how cache coherence protocol impedes NUMA scalability, and then I'll explain algorithmic consideration for saving the bandwidth in the design of persistent index. Now, let's talk about the cache coherence protocol. This is the internal structure of CPU and Optane DIMM. In the Intel machine, the default cache coherence protocol is directory cache coherence. Let me explain using a linked list example. Suppose that we have a linked list and node A is stored in NUMA 0's Optane DIMM and node B and node C are stored in NUMA 1's Optane DIMM. In this example, core 0 will conduct a linked list traversal from node A to node C. When core 0 reaches node A will be copied to the core 0's local cache. In this case, node A is stored in a NUMA local NVM space, so directory cache coherence information does not need to be stored. When core 0 reaches node B, core 0 copies the node B from NUMA 1's NVM space. In this case, the directory cache coherence information of NUMA 1 will be updated because node B is copied to the remote scan. When core 0 reaches node C, core 0 copies the node C from NUMA 1's NVM space. Similar to node B, copy of node C incurs the directory cache coherence information update. The problem is that the directory cache coherence information is stored in 3D point media. So the directory cache coherence information update incurs NVM writes which are harmful to the limited NVM bandwidth. Also, when an application reaches 870 MB from NVM, about 480 MB of NVM writes were also generated on the directory cache coherence protocol. A tentative solution to resolve the cache coherence protocol problem is to change the cache coherence protocol to SNP coherence at BIOS. We believe that the directory information should not be stored in NVM. We evaluate the persistent B+3 on both directory cache coherence protocol and SNP cache coherence protocol. We use 100% random lookup workload. As shown in the figure, the SNP cache coherence protocol shows better performance in read-only workload. Now, let's move on another guideline. Let me explain how the lookup operation consumes minimal NVM bandwidth. Let's first compare the NVM bandwidth consumption in two representative index design, B+3 and try, using an example of a lookup operation of a key AAC. In the B+3, the whole key itself is stored in the B+3 node. Thus, in lookup operation of B+3 to find the key, it needs to compare the keys stored in the node at each level. In this example, we first compare the given key to the root node key, and then it moves to the left child and compares the given key to left node key. Lastly, it compares the given key with the leaf node key. As a result, B+3 consumes 9 bytes. In the try, the keys are stored in a packed manner. The partial keys are stored in the path to the target leaf node. In this example, the lookup operation finds the partial key AA from the root node and then moves to the left child node. It will compare the given key to the partial keys in the child node. Finally, it finds the correct partial key from the node. As shown in the figure, try consumes 4 bytes. We also compare the performance and the amount of NVM reads of B+3 and try. As you can see, try shows less NVM reads and better performance than PACTree. So we propose that the index lookup operation should access the NVM in a packed fashion to save the NVM bandwidth. Now, let me explain our high-performance persistent range index PACTree, which is based on PAC guidelines. The key takeaway from PAC guidelines is that the fundamental performance limiting factor of a persistent index is the limited bandwidth and the slow latency of NVM. We propose that a persistent index should provide packed access to save the limited NVM bandwidth and asynchronous concurrency control to decouple the long NVM latency from the critical path. Following the PAC guidelines, we propose PACTree, a persistent and hybrid range index consisting of trie-based search layer and the data layer, which is a doubly linked list of B+3-like leaf nodes. We decouple the search layer and the data layer to fully exploit the PAC guidelines. It enables PACTree to use hybrid indexes, a critical aspect of performing packed NVM access and reducing the blocking time from the rebalancing operation of the persistent index. Let me explain how PACTree's lookup operation works using an example. Let's suppose that we are looking for the key ABA. Let me first introduce the target node. The target node is a leaf node that the correct data is stored. The search layer is variant of trie, so it embeds a partial key to the path to the location of the data. First, it starts from the root node, and then it compares the key with the partial keys of the trie node. Key ABA is in between key AA and key ATA, so the reader arrives at the first leaf node. We call this leaf node jump node. In this case, the jump node and the target node are the same, so the lookup operation is successfully done. Next, I will explain how PACTree's asynchronous update works using an example. Let's suppose that the case for insert operations of key ABB. Similar to the lookup operation, it first looks up the target node from the search layer. When it finds the target node, it acquires write lock for the target node. In this example, the target node is already full, so it will trigger the split operation. In the split operation, PACTree makes a new node and copies the half of entries to the new node. PACTree allocates the new node and copies the entries in a crash-consistent manner using SMLog. Please see our paper for detail. After copying entries, the new node is connected to the left and right sibling nodes, and the copied entries are removed from the overflow node, and PACTree unlocks the target node. In the split operation, a new leaf node was created, so the search layer also should be updated to point to the newly created node. The search layer is updated asynchronously by a background thread. The background thread uses SMLogs to insert the new entry into the search layer. Until now, we assume the case that the jump node and the target node are the same. However, since the search layer and the data layer are decoupled, the jump node and the target node may not be the same. Let me explain how PACTree tolerates this inconsistency using an example. Let's suppose that the split case we discussed in the previous slide. In this case, the split operation in the data layer is done, but the search layer is not updated yet. This example finds the key ABB. First, PACTree finds the leaf node location from the search layer. However, the search layer is not updated yet, so the result of the lookup operation in the search layer points to the sibling node of the target node. So, in this case, the jump node is the sibling node of the target node. PACTree can check if the jump node is the target node. If it is not, it will traverse to the left sibling node or right sibling node to find the correct target node. In this example, it moves to the right sibling node and finds the correct target node. By traversing the data layer, PACTree can tolerate inconsistency during the rebalancing operations. Let me show you our evaluation result. We evaluate PACTree on 2-socket 112 core machine with the real NVM hardware. Our machine has 3 TB of NVM. Each socket has 6 NVM DIMMs. We use YCSB benchmark, which is the standard benchmark for index structure evaluation. We compare the performance of PACTree against representative persistent indexes F3, Fast and Fair, and BG3. Our evaluation shows that PACTree shows better performance and scalability in both write-intensive workload and read-intensive workload. PACTree performs up to 4 times better than all the other persistent indexes due to the asynchronous update and packed NVM accesses. Other persistent indexes experience high latency in the critical path due to the structural modification operations. Also, BG3 and Fast and Fair suffers scalability bottleneck from the limited NVM bandwidth. F3 shows worse performance than PACTree because of a large number of hardware transaction aborts. We also conduct tail latency evaluation. We sampled 10% of the operation to reduce the measurement overhead. As you can see, PACTree shows low latency up to 20 times in write-intensive workload and comparable latency in read-intensive workload due to its asynchronous update, trie-based search layer, and B+3 leaf node like data layer. Let me conclude this talk. In this work, we proposed PAC guidelines based on our empirical analysis. The key away from PAC guideline is to access the NVM in a packed fashion to save the NVM bandwidth and exploit the asynchronous concurrency control to decouple the long NVM latency. We also propose a high-performance persistent index, PACTree. In PACTree, we decouple the search layer and the data layer. We leverage the trie-based search layer for packed access and exploit the asynchronous update to maximize the concurrency. PAC guidelines can be applied to other NVM software design beyond persistent indexes. For example, PAC guidelines can be applied to performance-critical system software such as file systems and database systems. Also, PAC guidelines except for guidelines on persistence overhead can be used for in-memory storage systems that use NVM as large volatile memory. Thank you for listening.